So thank you to the organizers for this invitation. My talk is going to be kind of a follow-up to the great keynote talk from yesterday on adaptive therapies, and kind of approaching the problem from a slightly different angle, and one particular aspect of it that we believe we can enhance. And just as a starting point, so our group essentially looks at a variety of different biophysical processes. We're primarily theoretical, and what connects all these things is kind of the fundamentally stochastic nature of the underlying biochemical processes. And this allows us to basically apply ideas from statistical physics to try to understand this in a mathematical way. And in the last couple of years, we've been kind of interested in how, in some sense, we can take these stochastic systems and influence them, control them, steer them toward a particular target. And this is kind of where the intersection with adaptive therapies came about. And this is a collaboration, a paper that was just recently published, which I'll be describing in this talk. And a particular shout out to Jake Scott from the Cleveland Clinic, the mathematical oncologist, who kind of got me into this entire area of modeling cancer evolution. And the motivation, which was well outlined yesterday by Bob, is in some sense, the ubiquity of Darwinian evolution in clinical contexts. So the classic example of this, of course, is bacteria evolving resistance to antibiotics. You can see this kind of from these, traditional bacterial lawn assays, where the bacteria, there's the ring of death around different types of drugs is clearly different for. So you can see basically different levels of resistance and susceptibility. And of course, this is, as described yesterday, this is also a major problem in cancer, right? And this is something that we're never going to be able to turn off evolution, but there might be a possibility of co-opting it and taking advantage of it to actually mitigate some of these problems that we get with the development of resistance. And so to kind of summarize this again, so kind of describe the kind of two-stage strategy which Bob talked about at the end of his talk. Imagine that we first apply a single drug, and we have the kind of classic development of resistance under that first drug. So if we do this in a very cartoon form, we have three different types here: A, B, and C. The size of the circles represents basically the size of the population. The color represents the fitness from more white which is low fitness to darker blue, which is high fitness. And as time progresses, we get the development of this resistant population. The more susceptible populations decrease in size until we have a population dominated by the susceptible, the resistant one. And if we now have a second drug, which happens to be extremely effective on this particular resistant genotype, so we take advantage of what's known as collateral sensitivity, which has been observed in a variety of both bacterial and cancer drugs. If under the second drug, our population C now is extremely susceptible, we can reduce it very quickly and hopefully eventually eradicate it. So the overall idea here is that with enough information, we can kind of rationally design drug therapies that allow us basically to use evolution as kind of a steering toward particular genotypes, which we then have ways of treating those genotypes. Now, the problem here as a practical level, and of course there are lots of different practical considerations here. First of all, how do we get enough information about the underlying system in terms of characterizing its evolution in order to be able to design these therapies? That's one level of kind of challenge. The challenge that I'm going to talk about today is a different kind of one, which is that overall, as a medical kind of approach, if we're going to use evolution, it is indeed a slow and very stochastic process. And if we want to, get to a particular endpoint, a particular target in a finite time, so if we set a given reasonable time frame for this, how do we achieve that, right? So is there a way, for example, of reaching a target reliably in a certain amount of time, essentially speeding up this entire process? So to tackle that, we're going to use the kind of classic conceptual framework for evolution, thinking about it as a process on a fitness landscape. And this is a one-dimensional cartoon of such a landscape, quite simplified, where you have a genetic sequence in some sense represented on one axis and fitness on the other. Of course, in reality, these landscapes are insanely multidimensional and extremely hard to visualize, but we're going to keep with the one-dimensional cartoon, just kind of give a flavor of it. And on this landscape, to kind of simplify all the mathematical complexities, there are essentially two factors that determine the dynamics. So there's a source of randomness that allows us to kind of diffuse along this landscape. That randomness provided by, for example, the finite size of the population, the random nature of mutations. And then there's an overall bias to this random walk. So where we tend to go up fitness peaks and due to natural selection, right? So in combining those two things, we get essentially stochastic dynamics on these types of landscapes. And this is a kind of a simple cartoon version of that here. And what makes the problem more challenging from the perspective of trying to steer this type of stochastic dynamics is that the landscape we're dealing with is not a static landscape. It's not, because we're changing the drug concentration over time. So what we're actually having is more of a seascape, right? Where the entire landscape is changing as we change the drug concentration over time, or other environmental parameters, right? They could be temperature, there could be oxygenation levels, nutrient levels, things like that. So how do we actually describe, and first of all, describe, and then second of all, control dynamics on these types of time-varying fitness landscapes? So what's interesting about this, and this is kind of where I kind of fell in love with the subject as a theoretical physicist, is that many of the mathematical descriptions that underline these kind of stochastic dynamics on landscapes, for example, one example is the Fokker-Planck equation, they have very close parallels to other descriptions in physics. So for example, the Fokker-Planck equation actually can be mapped onto the Schrödinger equation, which describes fundamental quantum processes. And it's not just unique to the Fokker-Planck. Even if you decided to not model this landscape as a continuous space, but rather as a kind of discrete Markov process, there are still ways of mapping those types of things onto quantum description. So there's this very neat kind of mathematical parallel that connects these kind of classical stochastic dynamics to quantum models. And what we did is essentially think about, well, can we then use some of these ideas from quantum mechanics maybe to help us to basically develop techniques to understand how to control these stochastic processes on such landscapes. So our inspiration here was a particular type of manipulation of quantum systems, which is used as kind of a hypothetical idea to do quantum adiabatic computation. And the way it works is, if you have the idea of the quantum adiabatic computer is you want to get to a particular final ground state which encodes the answer to a computational problem. And you typically start with a state of the quantum system that's easy to prepare. For example, if it's a spin system, all the spins are up because you applied a very strong magnetic field, and your system is in an initial ground state. And if you want to get to a particular final ground state, there is a theorem in quantum mechanics called the adiabatic theorem that says if you very slowly change the parameters of the system, meaning, for example, all the local magnetic fields, you're guaranteed to remain in the ground state throughout this entire process. Of course, this is in the limit of doing this infinitely slowly. But if you happen to do this at any finite speed, there's always the risk of essentially going into an excited state, and then there's going to be some possibility of error in reading out the final answer to the computation. So in the early 2000s, several groups of researchers basically figured out a way of essentially cheating. So if you really are interested in this, in maintaining the ground state of some original Hamiltonian, well, you can add a perturbation to it. You can add essentially a second term to the Hamiltonian. So we can think of this as modifying the fields that we're going to apply to the system. And these are called counter-diabatic fields. And what's beautiful about them is you can write them down in closed form and as analytical expressions. And if you apply just those precise fields, you can maintain the ground state of your, maintain the original ground state throughout the entire driving process. And hence you can get to that final point in finite time, regardless of how fast you drive it, right? So this is the idea that we're going to try to exploit and see if there's going to be essentially a classical analog of this type of counter-diabatic driving. So we want to essentially go from the kind of scenario where we're driving a quantum system along a certain trajectory of states to now, in a, for example, population genetics sense, driving a biological system through a certain trajectory of states, right? And what exactly does that mean in detail? I'll explain in a couple of slides. So The system we're going to start with is just, you choose your favorite model from population genetics. It could be a Wright-Fisher model, Moran model. It could be an agent, some kind of agent-based model. But essentially, what the fundamental processes that we're going to be including are, a population of different cells. There's going to be M different types of genotypes, and the cells can die, they can mutate. There's a birth rate related to the fitness of each type. And the key control knobs, the things that allow us basically to tinker with the evolution in the system, are essentially the fitness parameters of all the various types, which depend on drug concentrations. And we'll use that as our kind of basic and external parameter. Though again, it could be nutrients, it could be other environmental parameters. And throughout the examples, I'll show you essentially a one-dimensional parameter in terms of how we tune these fitnesses. But in principle, you can imagine doing a drug cocktail with multiple different concentrations. And so you can have a multi-dimensional control parameter as well, right? So we're not limited just to a kind of one-dimensional control picture. So you take this kind of evolutionary model, and to make it a little bit more concrete, what we did is we looked at an existing experimental system. So this was a transgenic yeast where a gene for antimalarial drug resistance was added. And what they did is they looked at 4 different mutations within this gene, conferring kind of in different combinations, different degrees of resistance to a particular antimalarial drug, pynimetamine. And you can think of all these different mutations. So you have 4 possible mutations, so 16 possible combinatorial types. We can label them from 0, 0, 0 all the way through 1, 1, 1. And the growth rates as a function of drug concentration are shown in this right panel. And for these types of systems, if you were to keep the drug concentration constant, the system would eventually reach a kind of equilibrium distribution of genotypes. And so, for example, on the left here, in terms of the size of the circles, those represent kind of the fraction of the genotypes in the population. You see, for example, an equilibrium distribution in the case of very, very low drug concentration. So here towards the left end of this graph, where this blue curve here, which corresponds to the genotype 1110, dominates the population, right? And then you have several others, who are still surviving, but with somewhat smaller growth rates. So this is a key thing to keep in mind. So for every single drug concentration, there's going to be some associated equilibrium distribution of genotypes, right? But we're not going to be there immediately. It may take some time actually to reach that evolutionary equilibrium. And in fact, we can actually do a simulation of this system and see how it works in practice. So if we were to change the drug dosage from very low to some intermediate value, so the drug dosage as a function of time is shown on the right. What you're seeing here on the left is on the top, well, just some snapshots at different time points of our system. And on the bottom, you see genotype frequency versus time. And we're plotting, several the most common genotypes in the population. What you see in the solid lines are the actual behavior of the system as a function of time. And in the dashed lines are what the equilibrium distributions are, right? So if for each individual drug concentration, there's going to be an associated equilibrium distribution, and that's shown here in the dashed lines. And you can see there's a general lag in the system. So as we change the drug, it'll be only, once we reach the final drug concentration in later generations, it'll be some time before the system equilibrates that final value. And so the solid lines reach the dashed lines. And you can see that in intermediate times, you're going to get a general discrepancy between the actual distribution of genotypes and the equilibrium one. So we show the actual here kind of in pink, the equilibrium in blue, and the overlap in purple. So here are 3 time points kind of in the middle of the driving. You can see that there's a discrepancy between the two, right? So if, let's say we wanted to do this and hit the target at kind of very quickly, right? So we wanted to reach this equilibrium distribution, let's say at 700 generations rather than 2000, how do we do that? And this is where this analogy with the counter-adiabatic driving in the quantum systems comes into play. Because the way we can think about this is in the target trajectory, which was a sequence of ground states in our quantum system, mathematically, it turns out that the exactly analogous thing in this kind of Fokker-Planck system in evolution is this sequence of equilibrium genotype distribution. So the equilibrium distribution is in some sense the analog of the quantum ground state. And as you're changing the field configuration in the quantum system, you're changing the ground state. Here, you're changing the equilibrium distribution. And so the idea of a control protocol, right, in the quantum case was, well, change the field strengths over time in order to hit the target, in order to reach what you want. And here, what you're going to try to do is basically have modified drug concentrations in order to hit that target. Now, I'm going to skip over all the technical and mathematical details. One of the nice aspects of this approach is that you can write down a closed form expression for these modified drug concentrations, right? Even for an arbitrarily complex evolutionary system, with multidimensional kind of control variables. So it gives a kind of a nice analytical form for the theory. And if we actually apply this protocol, so this is one example. So this modified drug protocol is shown in red. You can actually change the protocol to incorporate kind of physically realistic constraints. So here, for example, we put in a maximum dosage, right? Because it's unrealistic to imagine that we can go to arbitrarily large dosages. You can see now that with this calculated drug protocol here, we actually hit the targets. So the solid lines, the actual populations, match the dashed lines throughout the entire process of at every single time point, essentially, to good approximation. This is just for one drug, the pynimetamine, but we also checked it for other drugs that were experimentally characterized in the system, like cycloguanol. And in each case, you basically get this essentially approximate agreement between what your target is and what the actual population is. So this gave us a lot of optimism that this is as a proof of concept that this method might work. And one of the things that we're currently setting up is essentially experimental validation of these ideas. So we have an experimental collaborator, Carrie Samarat from Arizona State, who has these transgenic yeast strains, and she's now running experiments essentially to verify that these control ideas actually work. And in our collaborator Jacob Scott's lab, that we're also experimenting with applying this to bacterial systems as well, right? So this is kind of a building up in kind of various stages to eventually dealing with the complexity of maybe trying to apply this in cancer systems. So one last thing that I just wanted to mention is that these ideas are quite general because they're based on essentially having a biological process described using kind of stochastic mathematical descriptions, and so it's not unique to just evolution. It's actually, we have a preprint just from a couple of months ago where we show that these kind of control ideas, this particular method, is actually widely useful in different types of biophysical systems. So we can think of it as a framework for thinking, for example, about how protein chaperone systems work, where you have your control knobs are now things like external chemical concentrations, which vary over time, and you can guide a biochemical network through a sequence of states in this case. And here, of course, it's no longer a continuum description of the states, but it's a discrete kind of Markovian description, but the same methodology, the same basic idea holds. You can think of this even in the case of where the control knobs are for example, it's a single molecule biophysical experiment, like you're pulling with an AFM on a protein to understand something about the nature of its inherent folding landscape. And you can actually develop protocols. In this case, it's not a drug protocol, but rather how quickly you're pulling that stage as a function of time to basically control the probability distribution of the biomolecular extension. And it's known that if you keep that probability distribution looking essentially as if it's kind of quasi in equilibrium, the analysis of how do you extract different properties of the protein folding from that distribution becomes much easier, right? So there's a practical advantage to doing this. And the final thing is that we're, because again, these kind of landscape ideas are just really quite general in biology, we're thinking about this in other kind of contexts. So for example, developmental biology or ecology, right? So there's a lot of things to keep us busy over the next few years. So just as a final note, I want to thank all the collaborators on this particular project. From CASE, a combination of graduate students, and particularly Shamreen Iram, and various undergraduates contribute on this. And in the Cleveland Clinic, particular shout out again to Jake Scott. So thank you, and I look forward to the questions during the panel.